Today we're going to talk about electric charge. And we're really going to focus on the two main objects that carry charge for us, and those are protons and electrons. They're not the only objects that can carry charge, as you'll see later on in the lesson, but they are the two main ones, so that's the ones we will focus on. So first thing we're going to look at is a proton. A proton has a charge of positive 1.6 times 10 to the negative 19th coulombs. It's just a shorter way of writing that. So that's 1.6 times 10 to the negative 19th. Okay, but we write it a little bit shorter this way. Okay, and let's go back and look at this. Charge, we use the symbol Q to represent charge. Now, when we're talking about a proton, we often just write this symbol, P with a little plus above it. Okay, because then everyone knows what the magnitude of that charge is immediately, and they know that it's positive because of the plus. So you've got a positive 1.6 times 10 to the negative 19th coulombs. Now, from chemistry, you probably recall that amount of charge for a proton. You might also recall the mass. The mass is 1 and 67 hundredths times 10 to the negative 27th kilograms. And you most definitely are going to recall that a proton is found inside the nucleus. Okay, we all know that. So that's the first type of charge. The second type of charge is an electron. Again, charge is the symbol Q. When we talk just about an electron, we're going to use the symbol E with a little negative, because then we know we're talking about an electron here, and we already, again, know what the charge is going to be without even having to write it down. And that is negative 1.6 times 10 to the negative 19th coulombs. And when we start doing this, we're going to abbreviate coulombs with the letter C, okay? Just like we abbreviate kilograms with kg. So we're not going to write the whole word out. You might also remember the mass of an electron. It's 9.11 times 10 to the negative 31st kilograms, so it's significantly smaller than a proton, less massive. And it is found outside of the nucleus, okay? And there have been a lot of different diagrams and models for the atom, okay? But right now we're working with a model where we don't know exactly where the electron is, but we know it's in this cloud, and depending on whether it's in the S, P, or D state will tell us roughly where it is within that cloud, okay? So let's look at some other things about charge. Electric charge is conserved. So we've talked about conservation of energy in the past, both mechanical and then non-mechanical energy as well. So the total before is equal to the total afterwards. Same thing here. The total amount of charge in a closed system, that's important, stays the same. Okay? So the amount of charge there is beforehand, it has the same amount of charge afterwards. Now, that does not mean that we cannot create or destroy charge. It just means if we're going to create it, we're going to create a net charge of 0. So let's go ahead and look at one way that we're creating charge. Fermi in certain labs, they're creating charge, okay? And here's how it's happening. So this is a nucleus, okay? And then we have a photon coming in. And if it hits this nucleus in just the right way, there's going to be pair production. What's going to happen is we are going to get an electron that flies off in one direction, and then we're going to get this thing called a positron that flies off in the other direction. Okay? Now, an electron is going to have 1.6 times 10 to the negative 19th coulombs for a charge. The positron is going to have 1.6 times 10 to the negative 19th coulombs, but positive, the electron would be negative. So the net charge is 0. Just like beforehand, there'd be a net charge of 0. Now, you might be saying, okay, well, the photon and the nucleus just created these two items. They created mass. I thought mass was supposed to be conserved. Okay? Mass is conserved in chemical reactions. This is a nuclear reaction. And Einstein said that energy is equal to mass times the speed of light squared. Okay? So energy can turn into mass. Now, you might be wondering, why don't we know about these, positrons? Why don't we have them? Okay, why aren't they around? All right, well, that's because this is antimatter. And as soon as antimatter comes into contact with matter, those two things are going to annihilate. Okay, and what that means is that they are going to destroy each other. And when that happens, energy is going to be created. So here we created some charge, okay, and energy went into the mass of those charges. Then the opposite of that can happen, and when the antimatter and the matter come into contact with each other, they can annihilate each other, and you will get energy out. And you're going to get the same amount of energy out that would have went in to make it. And you can calculate that energy using Planck's constant multiplied by the frequency. So we can actually calculate that out. So let's look at this in a little bit more simplistic way that we might see more often. So that we can create charge, and charge can be destroyed. But just in general, charge is conserved in a closed system. So let's go ahead. We're going to look at, you've got a balloon, okay? And then we've got somebody's hair, all right? And you rub the balloon against the hair, and then the next thing you know, the hair is being attracted to the balloon. That's because maybe beforehand they're both neutral, but you rub the balloon on the hair, and some of the electrons jump over to the balloon, and now the balloon has a net negative charge, and since this was neutral before and some electrons left, this now has a net positive charge. So they both are charged. You could separate them and be like, oh, this is now charged, but overall, the number of electrons that left here that made this more negative is the same amount that left the hair and made the hair more positive, okay? So if you can put them back together and combine them, the net charge would go back to being what it was originally. The last thing we have here is that charge is quantized. So what does that mean? Well, it says the total charge is always a multiple of 1.6 times 10 to the negative 19th coulombs. So here's why this is. Let's say that we have a proton. So we've got one proton. Well, the charge is going to be 1.6 times 10 to the negative 19th coulombs, okay? Now, the next thing we do is we have two protons, okay? So now our charge has doubled, and it is 3.2 times 10 to the negative 19th coulombs. Notice we don't have 2. There's no 2 times 10 to the negative 19th. There's no 1.7. There's no 3. There's no 3.1. There's nothing in between these two, okay? And that's because we can't have part of a proton for the charge. So our charge is always going to be a multiple of the number of protons that are extra, or you could have extra electrons, okay? But it's always a multiple of this 1.6 times 10 to the negative 19th coulombs, at least for our purposes.